Okay, in this video, we're going to be covering the Henderson, Hasselbalch equation and titration logic. So, what you need to know is that pH is equal to pKa plus log of the concentration of A minus over HA. What does this mean? Well, okay, so pH is equal to pKa. And that's going to give you A minus is going to equal to HA. So in this, if you know that pH is greater than the pKa, that means you have more A minus. And this means that you have a deprotonated state. And if you have pH is going to be less than pKa, well, at this point, you have more HA. And what does this mean? It means that you have a more protonated state. So this is how you check every single one of your answers. So our first type of question problem we're going to do is we have to solve for P. You're going to solve for the pH given your pKa concentration. Okay, so what does this mean? So let's say that you have a buffer that contains the following. So you have it contains A minus is equal to 0.10 moles. HA is going to equal to 0.01 moles, and then the pKa is gonna equal to 4.5, and you want to find the pH. Okay, so how do you find the pH? Well, we can rewrite our equation, which is this. So let's move this down here. Okay, so this is our pH, right? So then we plug in our values. So our pH is going to equal to, what's our pKa? Our pKa is 4.5, and that's going to be plus the log of 0.10 over 0.01. Okay, now you simplify the ratio. This part is just going to equal to 10. And then you take the log of 10. And then the log of 10, this is just going to equal to 1. So then you're just going to have 4.5 plus 1 is equal to the pH, which is just equal to 5.5. And then you can check this. So you know that we had A minus 1 and HA that. So then you have, you know you have more A1 than HA, right? So that means that you have a pH that's greater than pKa, just like we saw up here. We saw this up here. So pH more A minus, deprotonated. A negative. So when your pH is greater than the pKa, that is that case. So that makes sense, right? Now, our second type is going to be when you solve for the ratio or your percent that is protonated / deprotonated. How do we do this? Protonated. Sorry about that. Okay, so let's say that we have a buffer and it has the pKa of 3.5 and has a pH of 4.5. So we want to find the ratio of A minus over HA. You also want to find the percent. You want to find the percent in A minus form. How do we do this? Okay, so we can rewrite our pH equation down here. So this was our pH equation, right? So now after this, what we want to do is we start with that equation. Then we plug everything in. So we have 4.5 minus 3.5. So what we're going to do is we want to subtract pK from both sides. So you have 3.5 is equal to log A minus divided by HA. So basically we subtracted that pKa. What was our pKa? Our pKa was 4.5. Our pKa was 4.5, yes. So then after this, what do? We can simplify. So we know that that's equal to 1. So then this is equal to log A minus divided by HA. Okay, so now we have to undo the log, right? So then we raise both sides to the power of 10. So then when we do that, then we cancel out that log. So then after this, we just have 10 to the power of 1 is just equal to 10. This is equal to 10. So then we know that these have to be equal, right? So then we can figure it out that the ratio is equal to 10. So that means we can say that A1 is going to be to 10. So then we can say the ratio is going to be 10 to 1. Now we want to convert it to percent. So 2%, we can get the total parts. So the total parts, that's going to be 10 plus 1, and that's going to be 11 parts. 11 parts. Now we want to get the percent of A minus. Well, how do we do that? We do 10 over 11, and that's going to equal to approximately 0.91, which is approximately 91%. Now we want to do the percentage of HA. So that's going to be 1 over 11. That's going to be approximately 9%. So then our ratio is going to be 10 to 1. And then it's going to be 10 to 1. Okay, and then it's going to be 91% deprotonated, which is A minus. And then here's a shortcut that you can memorize. So if you know that dpH minus pKa, that's going to equal to 1, right? So then that means that it's going to be around 90% A minus. But if you have pH minus pKa is equal to 2, then you can say that approximately 99% is going to be A minus. 99%. Okay, so now after this, let's do a titration curve problem. Titration curve. Okay, so this is when you use buffers plus pKa. Buffers plus pKa plus Henderson Hasselbalch. So this is combining 3 ideas. Okay, so let's say that you have a weak acid is titrated with a strong base. What is the pH at the half equivalence point? Okay, so we gotta reason this out. So first we have to find the half equivalence point. So in order to find this point, this means that we know that half of the HA has been converted to A minus. So that means that we know that, okay, so that means that HA is going to be equal to A minus because it's going to be the equivalence point. So now we plug into the then we have to plug into the Henderson Hasselbalch equation. And this is going to look like this. So you're going to have pH is equal to pKa plus log 1. Because you know the ratio of those two over, when you have the ratio of something over something is the same, it's just going to equal to 1. So then you evaluate this. Log of 1 is equal to 0 because 0 to the power of, yeah, that's going to equal to, yes. So then your final answer, you're just going to have that pH is equal to pKa. So your answer is that pH is equal to the pKa at the equivalence point here. And that's how you read the pKa off of the titration curve. Okay, so